Hello everyone, I am Mohamed Zanati and I'm here to talk to you today about the great things that WebRTC has been working on and how you can use them. WebRTC, it's what we call real-time communication, RTC, which is the ability to communicate live with somebody or something as if you were right there next to them. This can be audio or video or even just peer-to-peer data. One of the reasons is that WebRTC fills a critical gap in the web platform where previously apps like Skype could do something the web just couldn't. But now that turn around. Now it's a web of connecting WebRTC devices that can communicate in real time just by loading a web page. So here what WebRTC trying to do. To build key API for real-time communication into the web. To make an amazing media stack in Chrome so that the developer can build a great experience and to use network of connecting WebRTC devices to create a new communication ecosystem. And there are more than 1 billion users using WebRTC's enabled browser right now. Now let's dig into the APIs. There are three main categories of API that exist in WebRTC. First, getting access to input device, accessing the microphone, accessing the webcam, getting a stream of media from either of them. Secondly, being able to connect to another WebRTC endpoint across the internet and to send this audio and video in real time. Third, the ability to do this not just for audio and video, but for arbitrary application data. So because there are three categories, we have three objects. The first one, MediaStream for getting access to the media. Then RTCPeerConnection and RTC data channel. And we will get into each individually. So MediaStream represents a single source of synchronized audio or video, or both. Each MediaStream contains one or more MediaStream track. For example, on a laptop, we have got a webcam and a microphone providing video and audio streams, and they are synchronized. We can get access to these local devices using the getUserMedia method of navigator. So we just look at the code for that. You can see that getUserMedia takes three parameters, three arguments, constraints, success callback, error callback. For constraints, that takes video. Just enter the video and nothing else. And then in the success callback, they are setting the source of video using the streams that returned by getting user media. We can also use getUserMedia for input from microphone. In other words, we can use getUserMedia to provide a source node for web audio. It's a huge amount of interesting stuff that we can see with processing audio using web audio from the microphone. In the many protocols involved in setting up and maintaining peer-to-peer connection, the application API exposed by browser is relatively simple. The RTCPeerConnection interface, as shown in the figure, is responsible for managing the full life cycle of each peer-to-peer connection. RTCPeerConnection manages the full ICE workflow for NAT traversal. RTCPeerConnection sends automatic stun keeps alive between peers, and then it keeps track of local streams and keep tracks of remote streams. RTCPeerConnection triggers automatic stream renegotiation as required. RTCPeerConnection provides necessary APIs to generate the connection offer, accept the answer, allow us to query the connection for its current state. In short, RTCPeerConnection encapsulates all the connection setup, management, and state within a single interface. In order to establish a successful peer-to-peer connection, we must first solve several additional problems. We must notify the other peer of the intent to open a peer-to-peer connection, such that it knows to start listening for incoming packets. We must identify potential routing paths for the peer-to-peer connection on both sides of the connection and relay this information between peers. We must exchange the necessary information about the parameters of the different media and data streams. We must find out if the other peer is reachable and if it's willing to establish the connection. We must extend an offer, and the peer must return an answer as shown in the figure. WebRTC defers the choice of signaling transport and protocol to the application. The standard intentionally does not provide any recommendations or implementation for the signaling stack. Why? This allows the connection with a variety of other signaling protocols powering existing communication infrastructure, such as the following: Session Initiation Protocol, which is SIP, Application Level Signaling Protocol, widely used for voice over IP and video conferencing over IP networks, and ICDN, Signaling Protocol used for setup of telephone calls in many public switched telephone networks around the globe. Session Description Protocol (SDP). Assuming the application implements a shared signaling channel, we can now perform the first step required to initiate a WebRTC connection. Here is the code where the line 1 shows initialize the shared signaling channel, 2 initialize the RTCPeerConnection object, and 3 request audio stream from the browser, where the 4 register local audio stream with RTCPeerConnection object, 5 create SDB description of the peer connection, and then number 6 it's apply generated SDB as a local description of peer connection, whereas line 7 it shows the line to generate SDB offers to remote peer via signaling channel. SDB is a simple text-based protocol for describing the properties of the intended session. In the previous case, it provides a description of the required audio stream. The good news is WebRTC applications do not have to deal with the SDB directly. The JavaScript Session Establishment Protocol (JSEP) abstracts all the inner working of SDB behind a few simple methods calls on the RTC connection objects. Once the offer generated, it can be sent to the remote peer via the signaling channel. The initiator registers one or more streams with her local RTCPeerConnection object, creates an offer, and sets it as her local description of the session, and then sends the generated session offer to the other peers. Once the offer is received, he sets the initiator's description as the remote description of the session, registers his own streams with his own RTCPeerConnection object, generates the answer SDB description, and sets it as the local description of the session. He then sends the generated session answer back to her. Once his SDB answer is received by her, she sets his answer as the remote description of her original setting. With that, once the SDB session description have been exchanged via the signaling channel, both parties have now negotiated the type of the streams to be exchanged. Data channel. Data channel enables bidirectional exchange of arbitrary application data between peers. Once the RTC peer connection is established, connected peers can open one or more channels to exchange text or binary data. Here's the code. Line 1 shows register WebSocket like callback on data channel objects. Line 2 initialize new data channel with best offer derivative. Line 3 regular RTC peer connection offer or answer code. Line 4 register callback on locally initialized data channel. Line 5 register callback on data channel initiated by remote peer. The data channel API intentionally mirrors that of the WebSocket. Each established channel fires the same onClose, onOpen, onMessage callbacks, as well as exposes the same binary type. However, because data channel is peer-to-peer and run over more flexible transport protocol, it also offers a number of additional features not available to WebSocket. The preceding code example highlights some of the most important differences. Unlike the WebSocket, which expects the URL of the WebSocket server, data channel is a factory method on the RTCPeerConnection objects. Now we have got some JavaScript framework. In the last year with a great abstraction libraries to make it simple to build WebRTC app, just with a few lines of code. Example here from simple WebRTC. A little bit of JavaScript. There are to specify a video element that represent local video, and one represent remote video streams coming in, and then join a room just by calling the join room method. Peer.js. Peer.js do something similar to RTC data channel. Just create a peer and then on connection you can send messages, receive messages, so it's easy to use. Peer-to-peer architecture pose their own unique set of performance challenges for the application. One-to-one communication is relatively straightforward, but things get much more complex when more than two parties are involved, at least as far as performance is concerned. For signaling service, use a low latency transport. Provision sufficient capacity. Consider using signaling over data channels once connection is established. For the firewall and NAT traversal, provide a stun server when initiating RTC peer connection. Use trickle IC whenever possible. More signaling but faster setup. Provide a turn server for relaying failed peer-to-peer connections. And provision sufficient capacity for turn relays. For data distribution, consider using a supernode or dedicated intermediary for large multi-party communication. Consider optimizing the received data on the intermediary prior to forward it to the other peers. Data efficiency. Specify appropriate media constraints for voice and video streams. Optimize binary payloads, send over data channels, and monitor the amount of buffer data on the data channels and adapt to change in the conditions of the network links. For the delivery and reliability, use out-of-order delivery to avoid head-of-line blocking. If an order delivery is used, minimize the message size to reduce the impact of head-of-line blocking. Send small messages and set appropriate retransmission count and timeouts for partially reliable delivery. The right setting depends on message size, type of application data, and latency between the peers. Thank you.